Imagine a giant propeller spinning underwater. It pushes water, propelling ships forward. But what happens when the pressure around the propeller drops drastically? The water, no longer able to hold its liquid form, transforms into vapor. Tiny bubbles filled with nothing but water vapor emerge from the depths. This, my friends, is cavitation. Cavitation, the formation of vapor cavities in a liquid, is a fascinating phenomenon with significant implications for engineering. These vapor bubbles, though seemingly harmless, can implode with incredible force. Imagine the pressure of an entire ocean collapsing on a single point. That's cavitation for you. This implosion, while invisible to the naked eye, can cause significant damage to machinery. Think of it as a continuous barrage of microscopic explosions, slowly but surely eroding even the strongest metals. But cavitation isn't just about destruction. Understanding this phenomenon allows us to design more efficient and durable machines. That's where the magic of computational fluid dynamics, CFD, comes in. Let's dive into our first project, where we explore the world of propellers. These marvels of engineering are essential for propelling ships, submarines, and even aircraft. But cavitation can significantly hamper their performance, leading to reduced efficiency, increased fuel consumption, and even catastrophic failure. Using ANSYS Fluent, a powerful CFD software, we can simulate the flow of water around a propeller. This allows us to visualize the formation and collapse of cavitation bubbles. By tweaking the propeller's design, we can minimize cavitation and its adverse effects. Imagine being able to design a propeller that glides through water with minimal resistance, maximizing efficiency and reducing noise. That's the power of CFD simulations in action. Through these virtual experiments, we can optimize propeller designs for various operating conditions, ensuring smooth and efficient operation. Next, we journey into the heart of power generation turbines. These engineering behemoths convert the kinetic energy of fluids like water and steam into mechanical energy, driving generators and powering our world. But cavitation poses a constant threat, potentially damaging turbine blades and reducing energy output. ANSYS Fluent allows us to create a virtual replica of a turbine, complete with its intricate geometry and operating conditions. By simulating the flow of water or steam through the turbine, we can identify areas prone to cavitation. This knowledge empowers us to make informed design decisions. Imagine being able to predict and prevent cavitation damage in turbines. This translates to increased turbine lifespan, reduced maintenance costs, and a more reliable energy grid. CFD simulations are instrumental in ensuring the smooth and efficient operation of these powerhouses of our modern world. Before we delve into the intricacies of pumps, let's take a moment to appreciate the role of inducers. These unsung heroes of fluid mechanics play a crucial role in preventing cavitation in pumps. Inducers are essentially axial pumps, placed before the main pump to increase the pressure of the incoming fluid. This preemptive strike against cavitation ensures smooth and efficient pump operation. Using ANSYS Fluent, we can simulate the flow of fluid through an inducer, analyzing its performance under various operating conditions. By optimizing the inducer's design, we can minimize pressure drops and prevent cavitation from rearing its ugly head. Imagine a world where pumps operate silently and efficiently, thanks to the carefully engineered inducers that pave the way for smooth fluid flow. CFD simulations allow us to design and optimize inducers, ensuring the reliable operation of pumps in various applications. Pumps, the workhorses of many industries, are responsible for transporting fluids from one point to another. From pumping water to our homes to circulating coolant in engines, pumps play a vital role in our daily lives. However, cavitation can significantly impact pump performance, leading to reduced efficiency, increased wear and tear, and even catastrophic failure. ANSYS Fluent allows us to peer into the inner workings of a pump, visualizing the flow of fluid and identifying areas prone to cavitation. By adjusting the pump's design, such as impeller shape and operating speed, we can mitigate cavitation and enhance its performance. Imagine a world where pumps operate silently and efficiently, delivering fluids with unwavering reliability. CFD simulations empower us to design and optimize pumps for various applications, ensuring smooth and efficient fluid transport in countless industries. Our final stop takes us to the cutting edge of technology: water jets. These powerful tools utilize a high-velocity jet of water to cut through a variety of materials, from metal to stone. Cavitation plays a critical role in this process, enhancing the cutting power of the water jet. Using ANSYS Fluent, we can simulate the formation and collapse of cavitation bubbles near the water jet nozzle. This allows us to optimize the jet's design and operating parameters to maximize its cutting efficiency. By understanding how cavitation influences the jet's behavior, we can achieve cleaner cuts and improve cutting speeds. Imagine a world where water jets can cut through any material with incredible precision and speed, all thanks to our understanding of cavitation. CFD simulations are instrumental in unlocking the full potential of this technology, enabling us to design and optimize water jets for a wide range of applications. In each of these projects, we've witnessed the power of CFD simulations in tackling cavitation. But what exactly happens behind the scenes of these virtual experiments? Imagine a digital replica of our physical world, where we can manipulate variables and observe the consequences without any real-world risks. CFD simulations break down a complex problem, like fluid flow, into millions of tiny parts. These parts, called cells, are governed by mathematical equations that describe the fundamental laws of physics. By solving these equations simultaneously, we can predict how the fluid will behave under different conditions. It's like having a crystal ball that allows us to peek into the future of fluid flow. We can see how changes in design, operating conditions, or even fluid properties affect the system's behavior. This predictive power of CFD simulations is invaluable in making informed engineering decisions. Now, you might be wondering, how do we actually perform these simulations? That's where ANSYS Fluent comes in. This powerful software provides all the tools we need to create, run, and analyze CFD simulations. Think of it as your virtual laboratory for all things fluid dynamics. With its intuitive interface and comprehensive features, ANSYS Fluent allows us to define the geometry of our system, specify the fluid properties, and set up the boundary conditions. It's like building a virtual model of our experiment piece by piece. Once everything is in place, we can hit the run button and watch as Fluent solves the complex mathematical equations that govern fluid flow. The software provides us with a wealth of data and visualizations, allowing us to analyze the results and gain insights into the system's behavior. From the depths of the ocean to the cutting edge of manufacturing, cavitation is a phenomenon that engineers must contend with. But armed with the power of CFD simulations and tools like ANSYS Fluent, we can unravel the mysteries of this complex phenomenon. By understanding how cavitation forms, evolves, and impacts our designs, we can develop innovative solutions that mitigate its adverse effects. CFD simulations empower us to optimize designs, improve efficiency, reduce maintenance costs, and push the boundaries of what's possible in various fields. So the next time you see a ship gliding through the water, a turbine spinning gracefully, or a water jet slicing through metal, remember the silent force of CFD simulations working behind the scenes, taming the destructive power of cavitation and shaping a better future.